Okay, so and again, a differential equation is just an equation with a derivative in it. So actually, I'll circle that, highlight that, and just make note of that. I think I mentioned that in the video, but a equation with a derivative. Basically with dy dx in it or y prime in it. And it doesn't have to be explicit, it could be implicit, meaning x's and y's are all mixed in. Okay, so let's take a look at down below question number 1. And this is more just conceptual. Let's say you guys were given y equals 0.5x squared, which is graph right here, y equals 0.5x squared. And I asked you guys, and we're working a little bit backwards here, but if I asked you to find the derivative of that, can you guys type it into the chat for me? Can you type into the chat, what is the derivative of y equals 1/2 x squared? And I did see the question about how do we know whether to separate or not. I'll address that when we get to the third page. And again, remember y prime dy dx, this is the slope of tangent line. Okay, so if I was given, let's work a little bit backwards here. Dy dx is equal to y prime, right? So when we're talking about separable differential equations, we're usually going to replace dy dx or y prime with dy dx equals x. And someone did ask, like, how do you know whether or not you can separate? You would have to treat dy dx, dy as a change of y, and dx as a change of x, and you can separate doing, if these were variables, algebraic operations. Okay, so it has to be like legally, you can separate it through like multiplying or manipulating the equation and isolating such that on the left you guys have y and on the right you have just x. So with this one, I mean, I know we can integrate without separating, but if I were to separate, I would multiply both sides by dx. And you kind of get an expression that's similar to your u substitution expression. And then on the left, I see that it's all just y's. On the right, I see that it's all just x. And the video that you guys watch, obviously much more difficult than these types of problems here, but you can integrate both sides. If you integrate 1 dy, you're going to get y. If you integrate the right-hand side, you get x. And then because it's a general antiderivative, x plus c. Okay, so x plus c eventually is the solution, and we want to be able to integrate and solve it this way because then it's an exact answer to what the solution curve is. However, let's say we were relying on just the fact that we know y prime is equal to x and that this is the slope of the tangent. Okay, so we're going to pick a few points. Let's say you guys picked along this column right here, the x value is 0. Right? Let's calculate the slope here. If I were to plug in 0, x equals 0 into here, what is y prime equal to? Oh, thank you, you guys. Only one person caught that I integrated and I didn't actually integrate. Thank you. X squared over 2. Thank you, Brandon. X squared over 2. That's the solution curve. That's why you guys see a parabola. Okay, thank you. So when you guys plug in x equals 0, you get y prime is equal to 0. So let's go ahead and say, okay, well, the slope at 0, 0 is going to be 0. The slope here is going to be 0. The slope here is going to be 0. Slope here is going to be 0. And again, all of these x values have a value of 0. And if I plug it into here, I get the slope of the tangent line at that point should be 0. Okay, can I have you guys do it at x equals 1? Can you guys plug in x equals 1? What do you guys get for the slope when you guys plug in 1? A lot of kids, by the way, Calc AB kids too, they like this chapter. It's pretty easy to do slope fields. All you're doing is plugging in that particular value. And sorry, we're calculating the slope of the tangent. So this is the slope of the tangent line. We're going to plug it into here. So we should get 1. And if you guys think of 1, what does a line with a slope of 1 look like? It should look like a tangent line segment with a 45-degree angle. So all through this column, we're going to have slope values of 1. And if you guys watched the curve that was the solution 1/2 x squared, you see that it does follow along that pathway, that the tangent line that goes through 1, 1 should, or the function that goes through it should follow that pathway. Okay, so then let's try the left-hand side. Can you guys go ahead and calculate what is the slope at x equals -1? And go ahead and sketch that into your graph, that column of slopes. So -1 would indicate that it has about a 45-degree angle. And once again, we see that we're coming up with the slopes of basically a parabola, right? The slopes of a parabola. And then can I have you guys now type in what the slope is at x equals 2? What is the slope at x equals 2? Okay, how would you guys draw this one? Maybe draw this, describe how you guys would draw this differently than x equals 1. What does that mean about the slope if it's 2? Well, Brandon was exact. Is it steeper or is it flatter? Okay, I think the more of you guys are writing in steeper, I had maybe a few say flatter. The higher the number for the slope, the more steep the slope is. Your rise is 2 versus your run is 1. So this does not have to be exact. You just want to make sure that your slope is more steep than the one before that. And I'll talk about how the AP readers will grade this on the other side. So now we go through, this side is going to be -2, and so on and so forth. And so what we see is that had I told you guys the initial condition was 0, 0, you would use the slope field. If they say sketch the solution curve, you would sketch the parabola such that it follows the movement of the slope field and make sure that you pass through the initial condition could have been, make sure it passes through 0, 0. So that's an example of a slope field type problem. Okay, so what family of functions seem to match all the slope fields? Well, in theory, if I had told you guys, can you sketch it such that it goes through, let's say, a different initial condition of 0, -1, then we see that, and you guys don't have to do this one. I'll just kind of like map out a few, but you guys can see that I would follow the trend, and each initial condition that changes, we see we have a whole family of functions, of parabolas, such that when I take its derivative, I get back to dy dx equals x. Okay, so these all just differ by that constant, that plus c signifies the whole entire family of functions that such that its derivative is equal to x. And remember that if I were to take the derivative of this, the derivative of the constant is just 0. So we get back to y prime equals x. I think I told you guys that. The initial condition of the function graph there is 0, 0. And it could have been a different value. If I had given you guys 1, it would have been 1/2. Okay, go ahead and go to the next page now for this. So similar type question, and let's assume that you guys are going to make sure that the graph goes through 0, 0. Can I have you guys go ahead and sketch the function, which is the solution curve, such that it goes through 0, 0. And as you guys do that and try to figure out what the graph looks like, a couple things to note: the AP readers are not going to graph or ding you guys if one parabola is like wider than the other. So long as you guys make sure you go through and match the movement of the slope field and say like you should have gotten some type of parabola for this one. Whether your parabola is a little bit wider, a little bit narrower, it doesn't matter. They're really just making sure that you use the slope field to help guide you, and they're not going to ding you unless you guys have, and again, don't follow my movement here, but if you guys go and you guys graph something like that, or you graph something like this that doesn't follow the movement of the slope, those would be indicative of a wrong answer. So just make sure that you guys are following the general flow. You should be good with sketching the solution curve, and also obviously if they give you an initial condition, making sure that it goes through that point. Okay, so fairly easy on those slope field questions. on the slope fields, you're not going to be given as many points as this to fill out. At most, they'll say, can you fill out the slope field given dy dx equals this for 9 points. Most of the times it's between 6 or 9 points that they have you guys graph. Here, since what we notice is that it's the same for all x values of the same value, like so all x equals zeros are the same here. This is something that's fairly easy to do. So we'll do one together. Here, dy dx equals 2x. Okay, so if I plug in, and you guys can create a table of values if you like. This one is easy enough that you don't have to. But you could, come up with one if you like. But at x equals 0, we can see if we plugged into that, what's your slope at 0? When x equals 0, what's your slope? Okay, good. And then go ahead and start to graph, you guys. So I know slope fields are, if anything, tedious, but easy to do. Okay, so we want to make sure that makes sense. All of the slopes through x equals 0 is 0. Can you guys tell me what the slope is for 1? Good. And then go ahead and graph. And then we know at -1, it'd be the opposite direction. And just in the chat, can you guys type for me after you finish the -1 and 1? If I were to integrate that, what family of functions would I get? What should I anticipate the solution curve to look like? What family of functions would it be? Good. Yeah, you have a derivative being linear. So the antiderivative, that should be a parabola. So when I'm sketching my slope fields, I should anticipate that the movement of the slopes should map out solution curves that are parabolas, right? A parabola. The differential equation is linear, but the solution curve is a parabola. And then we'll do one last one here, you guys. At x equals 2 and -2, we should see, and I probably drew that one a little bit too steep, but something that's steeper than the one that I had before. I was just trying to draw it so it's steeper here. But yeah, so you guys are doing 4, -4. And again, they're just looking that you guys have drawn it. Really, did you go in the right direction? So if you graphed a slope field question and it's a negative slope, but you did a positive slope, things like that. Okay, so let's see what we get with the bottom one now. Can I have you guys tell me what the slope is at x equals 0 for that one? At x equals 0, what's the slope? Okay, so if we have a fractional value less than 1, we want to make sure that it looks flatter than 1, right? So just to the best of your ability, and it's like basically rise 1, run 3, just make it flat. Okay, we'll go backwards here. Can I have you guys tell me what the slope is at -1? At -1, x equals -1. And go ahead and technically, if it's bigger than 1/3, so it should be slightly, probably not really something that you guys can really distinguish between the previous one, but it should be a little bit steeper than 1/3. And then at -2, we have, at -2, what do we have? Okay, perfect 45-degree, 1, right? 1. Okay, here's the question now. What's occurring at x equals -3? What's your slope at x equals -3? Good, Brandon. Ooh, I like all 3 answers. The first 3 answers I got were vertical tangent, asymptote, and undefined slope. Very nice. Yeah, so it's undefined, which means that it's all those things, right? You guys are going to draw a essentially a vertical asymptote, a line segment with an undefined slope. And so you guys know graphically, if I were to look at 1 over x plus 3, that's that it's going to have a vertical asymptote there. So when I sketch my solution curve, I'm going to make sure I'm not going to go through x equals -3. And then we'll finish off with the other value on to the left of -3. So -4, can you guys tell me what the slope is at -4? Okay, and go ahead and finish that off. 45-degree angle going the opposite direction, -1. So perfect. So to the left of your function, if you guys follow my cursor, you might get that your solution curve looks like this. Okay, that y equals that if I were to solve and then it says it has to go through this point. But to the right of that, it's going to look slightly different, right? And so the solution curve is still a family of functions. They all have this as its derivative. It's just that if you are given a different initial condition, you want to make sure you use the slope field to help guide you guys on as to what it would look like. So we're going to take what we learned right now, put it together with what the video was on, and hopefully kind of draw some connections. So I was literally going to flip over my iPad right now. Can you guys go ahead and go down? I was meaning to flip the page and I was going to turn my iPad over. Oh my goodness. Okay, so sketch the path of the unique solution if the graph passes 0, 1. So here is a problem where they give you guys the slope field, they give you guys an initial condition, and then they ask you to sketch the, so I'm going to do this in one color. Okay, so going through 0, 1 means that I'm going to find the coordinate point 0, 1. I'm going to make sure that I go through 0, 1 and then just do the best that you guys can to follow the movement of the slope fields. And if you guys can type into the chat, what function does that appear to be? What family of functions does that appear to be? Good. For those typing it out, that is correct. Yes. Okay. So exponential was all I was looking for. It's some appears to be, let's just write that here, appears to be exponential. Okay, if the question, however, asked, can you make sure that the function passes through 0, -1? Can you guys go ahead and sketch, how would that look different? So we want to make sure we go through 0, -1. And this time it looks like it's a reflection of the exponential function across across y equals, or sorry, across the y-axis, right? So it's still exponential. So that's the solution curve that passes through 0, -1. Oops, I think I wrote that in the wrong spot, but this is exponential. And so let's say that they actually gave you guys this at the beginning, and they said, sketch the slope field. The slope field that you guys see here is the slope field represented by dy dx equals y. Notice that dy dx equals y is now in terms of y, and that's okay. Okay, that's what you guys were working on the previous video, was solving for it the way that we're going to do it right now. So this is an example for the video that if you missed the video assignment, you're going to go back and watch that because the problems are much more complicated than this one. But when they say verify your guess analytically, here's the thing with differential equations. There's only a small selection of differential equations that you guys can actually solve, like analytically. The way that they're saying it is through separation of variables. So this is through separating variables. And I'm going to walk through how they would award the point for this. I don't think I did it in detail on the video assignment, but let's say this was a AP problem. And so the question that was asked before is, how do I know when things are separable? Okay, so let's say, let me first start off with, and you don't have to write this down, but just so to give you guys an idea. Okay, so if I asked you guys to try to separate the variables on this one, okay, if dy and dx are differentials that represent variables, the first move would be, okay, I would multiply dx to get, you want dy and all the y's on one side, you want dx and all the x's on one side. So this is going to cancel out, and you guys get dy equals x minus y times dx. So is there a way for me to move the y variable over to the other side, but keep the x variable over on the right? What do you guys think? Yes or no? Can I separate these variables? Can I move the y without moving the x? Here's a good question. Someone said, can I add y to both sides? Technically, if dx is a variable as well, if you distribute the dx, you get x times dx and then minus y times dx. So there is no way to add the y over without adding dx over as well. So this is an example of one that you guys could not separate. Okay, typically you can only separate through like multiplication or division, not through addition when you get to this step right here. Okay, so this is, and you know, I think it just takes a bit of practice to get familiar with, well, can I separate or not? And again, very few questions are you're able to solve analytically, solve through separation of variables. So here, let's take a look at one that you can. So we're going to solve this one analytically through separation of variables. So go ahead and write dy dx. And for those of you guys who already watched the video, go ahead and see if you guys can do this. And I'm just going to guide people through as though they haven't seen this yet. So what we're trying to do is, again, separate the x's and y variables. So times both sides by dx, that's going to cancel out the dx. I get 1 dy equals y times dx. Now the y is over on the right, we want it over on the left. This is through multiplication. So I'm going to undo by dividing by y. Very nice for those of you guys who have already gotten the answer. Okay, so then right now you guys have 1 over y dy equals 1, technically 1 dx. At this point, this is considered, you guys have separated the variables. So actually, can you guys mark on here so that you know how the AP readers would grade you guys on this? By the way, these are the perhaps the most, I guess, punishing, I can't think of the word right now, brutal punishment if you don't get this first step. Okay, if I look at the problem and I don't immediately separate, you would lose all 6 points. The other types of free responses, you can like regain yourself at some point, like come back and answer B correctly without necessarily answering A correctly. But if this is all part of part A and you don't separate the variables, you lose all 6 points. So the first point is so important on this one. It would be 1 point for separating the variables. Okay, and then the second point would be awarded for you guys integrating both sides. So at this point, I'll just switch colors here. You guys are to integrate both sides. And this is going to be the second point, integrate. Okay, so I get ln of absolute value of y. Over on the left, we're going to integrate both sides. Integrate 1, we get x. And then it's to the side of the x that you add plus c. You do this because technically you have a plus c over on this side, and then you have a plus c on this side. But if I subtracted some constant over to the other side, I still have that this constant represents, kind of like encompasses the constant that was supposed to be on the left as well. So both of those have constants. Okay, and then at this point, once you guys, it's at this step right here that I recommend that you guys, if you have an initial condition, you plug back in to solve for C. So I'm sorry, I don't think I provided the initial condition, but let's say that the initial condition was the 0, 1. So let's up here, let's write IC, and I'm using the initial condition up above here for A. Okay, so initial condition was 0, 1. So what we do with the 0, 1 is that's going to allow us to solve for C. So we're going to plug 0, 1 in. When you guys do that, ln of absolute value of 1 equals 0 plus C. Please know this, while I have students at the end of the chapter still messing up on ln of 1. ln of 1 is e to the what power is equal to 1, and that is 0. So nice and easy, our constants equal to 0. Okay, so take the equation that you guys had right here, bring it down. We have ln of the absolute value of y equals x plus c, but c is 0, so we have just x. Okay, how do I undo ln? What's the operation that will undo ln? That process is called exponentiate. So if you guys hear me say the word exponentiate, that's just taking e to the power of both sides. That's to undo the ln. So right now, the e is the base, and the ln of absolute value of y is the exponent, and x is the exponent. So that's going to allow me to undo that. Then I have absolute value of y. Don't drop the absolute value. So I'll kind of point out mistakes that can occur along the way, and this is mistake number one, is dropping it too soon, dropping the absolute value too soon. Okay, so absolute value is still part of the answer. And then you have y equals, to drop the absolute value, you guys are going to add the plus minus on the other side and say that there's two possible solutions. Positive e to the x is a possible solution, and negative e to the x. When I go back to my, and sorry, let me give you guys a few seconds if you're still trying to catch up. Can you guys look at the two solution curves that you sketched above? One went through 0, 1, and one went through 0, negative 1. This encompasses both solution curves. So my answer should, if they provided me the initial condition at the start, which they did, this solution curve must pass through e to the x. So you have to make that selection. So this is the, I feel like a lot of times students will get to the free response, they do everything beautifully, and then they leave, they box this as their answer. Remember, if it's an initial condition at the beginning, that solution curve, your particular solution, has to go through that point of 0, 1. So your actual answer is just the positive version of e to the x. So let me give you guys what some of the other point values are. There's a +1 for plus c. There's a +1 for plus c. There's a +1 for the initial condition. So +1 for solving for the initial condition. And +1 for finding y, which is here, and plugging c back in. So finding y and including plus c, including your c value.